Hello everybody and welcome to exercise 4 on page 21 of the workbook. Let's take a minute to read this question together. So let f of t equal 1.3 to the t be the population of a bacteria colony in hundreds after t hours. They would like us to use the table method to approximate f prime of 0, that is the derivative of f at 0, accurate to the nearest 0.001, and then finally to give an interpretation of our answer. Okay, well, let's first take a look at the graph that they're giving us over here to the right. Okay, so we're talking about population as a function of time. Notice that t is down here on the horizontal axis, and we're measuring that in hours, it looks like. Okay, and then p is representing population of bacteria. So bacteria would be our units there. And this f prime of 0, remember, that's notation for the derivative. The derivative graphically is the slope of the tangent line. And in our case, the slope of the tangent line at 0. I'm just going to draw in that line. Okay, and label it. So graphically, what we're being asked to estimate is the slope of t, that tangent line. Okay, well, let's start with our definition of the derivative. So f prime of 0, we discovered that we could describe that as a limit. Okay, so I'm looking back a couple of pages in the workbook here. This is the limit as h goes to 0 of f of a plus h. Our value of a is actually 0 in this case. So we're going to get f of 0 plus h minus f of 0 over h. We're just plugging in zeros everywhere that we saw a's in that formula. Okay, and to do the calculation here, starting with 0 plus h, that's a value of t that we're substituting into our function. So everywhere that you see a t, you're going to put a 0 plus h. Okay, and 0 plus h is really just h. So that would look like 1.3 to the h. All right, and then we come to f of 0. So now we want to plug 0 in to our function. And what do we get if we take 1.3 to the 0? 1.3 to the 0 is actually 1 because any number to the 0 power is 1. So that f of 0 just becomes a 1, okay, over h. All right, so that's the limit that we want to calculate. So I've got a question for you at this point. Could we just substitute h equals 0 in to calculate that limit? Would that work? The problem is we have a denominator of 0, and so we can't just directly plug 0 in for h. Okay, so what could we do instead? Well, we've seen in a couple of problems that sometimes you can algebraically simplify and get that h in the denominator to cancel, but in this case, there's really not anything we can do to simplify. Okay, and so that's why in the problem they suggested that we use the table method. Okay, that's a way of approximating a limit. This goes back to what we talked about earlier on in the course. Okay, so we're going to estimate this limit numerically by choosing a list of values for h that get closer and closer to 0, and then to take those and substitute them into the thing that we're taking the limit of, 1.3 to the h. This is trying to write a little bit small here. 1.3 to the h minus 1 over h. That's what we're taking the limit of. Okay, so because h is approaching 0, we want to choose a list of numbers that gets close to 0. So maybe 0.1, 0.01, okay, and so on. We're just going to try to get a feel for what this 1.3 to the h minus 1 over h approaches as h gets small. All right, so at this point, you would go to your calculator, take h equals 0.1 and substitute it into this expression. I'll let you confirm that if you do that, you're going to get 0.266 if you round off to 3 decimal places. Okay, then you do the same thing for the other 3 numbers. If you substitute 0.01 in for h, what you're going to come up with is 0.263. Okay, and then one question that you might ask when you're doing this is, how far do we go? How many numbers in our table do we need? Well, generally you go out far enough so that the numbers that you get out stop changing. Okay, so kind of with that in mind, if you plug in 0.001, you're going to get 0.262. That number is not the same as 0.263, the number to the left of it, so we need to keep going. And what you'll discover if you plug in 0.0001 is that if rounding to 3 decimal places, you do get the same number. So the fact that these two numbers are the same suggests that if we kept going and made h even smaller, we're probably going to just keep getting 0.6262 over and over again. Okay, so our best estimate of f prime of 0 is 0.262. They wanted an interpretation from us as well, so we should think about units here. What are we measuring? Well, remember that the derivative is about a slope, the slope of this tangent line t over here, so its units should be rise over run, bacteria per hour. Oh, and actually, I just noticed a slight error that I made here. It's not just bacteria, it's hundreds of bacteria in the problem if we read it carefully. So this would be 100 bacteria per hour. Okay, space is a little bit tight here, so I'm going to do my best to sneak an interpretation in here. They wanted an interpretation of our answer here. So we have just measured a growth rate at t equals 0. Our colony is growing at a rate of 0.262 bacteria per hour. Okay, 0.262 bacteria per hour. Or we could write that by, we could move the decimal point over and say that that's equivalent to 26.2 bacteria per hour. Either way, 0.262 is the same as 26.2. All right, and I think we have finished the problem.